All right, so check this out. Block A, block B, and something connected to the wall. It's all connected through a string or a rope or whatever it is. And apparently there's friction. I'm just going to put a little arrow there to remind you. All right. What is the coefficient of static friction between block A and the surface? That's what the question is. All right. I have a question, Julia. If block A were made of ice, that means there's no friction. What would you expect to happen for this thing?
If there was no friction, then
I mean, look at the setup. How would you expect that thing to move? Give me your...
well, I'd expect it to move in the direction of block B, or the weight and the tension
I would
in the
expect.
right direction.
I would expect block B to fall down.
Right.
I would expect block A to move to the right.
Yeah,
Does that make
because
sense?
that's where all the tension is.
Yeah, the tension is pulling to the right.
Right.
So I would expect that block A moves to the right. That must mean, like, without looking at this problem, before I even read that there was friction, I said there's got to be friction on this thing or this thing is moving, right? So I would say that there's a friction force pushing this way, force of friction. Are we cool with that?
Yeah.
The reason why I say it's pushing this way is because the block has a tendency to want to move that way. And the force of friction will always push in the opposite direction of where the block will want to move, or is moving. If the block's moving to the right, the force of friction will push to the left.
Right.
In this case, the block's not moving at all, but the block will want to move to the right. So the force of static friction is moving to the left.
Because friction opposes motion.
Friction opposes motion, but in this case there is technically no motion, so that's why we're talking about static friction as opposed to kinetic friction.
Right.
So maybe I'll put it, instead of an FF, which stands for force of friction, I'm just going to put FS, which tells me that's the force of static friction.
Gotcha.
Okay. Okay, here's what my thoughts are. I'm going to do a sum of the forces in the x direction is equal to mass times acceleration in the x direction on block number A. Is there acceleration in the x direction on block A? Read the problem carefully. I'll wait.
No, because it's static friction, so there's no motion.
Because they told us there was no acceleration. All right. What forces do you see on block A?
Tension and static friction.
Tension minus static friction is equal to 0. So static friction is equal to tension. Static friction is mu times the normal force is equal to tension. Instead of writing a big N, because I sometimes get that confused with newtons, I'm going to write F little n. Cool?
Gotcha.
All right. Looking at this, can you tell me what F of n is equal to right off the bat?
Mass times gravity.
Mass of A times gravity.
Right.
Right. And technically, I should have done the sum of the forces in the x direction on A. But if you look at it, the only forces that you see sum of the forces in the y direction on A. But if you look at the picture, the only forces that I see is the weight of A and the force normal in the A direction. So those must be the same if it's not accelerating up and down. That's what my thought process was. I'm sure that's what you thought if you were just able to throw out the answer like that.
Yeah.
Good. Good, good. You're getting an intuition for this. Now, I'm trying to solve for this mu s right here. But I don't know what tension is. So I'm gonna have to do some side work here. Because I know what MA is, I know what G is. I don't know what T is. Once I figure that out, I can easily get mu s. To get tension, I'm going to take a look at this piece right here. Okay? I'm going to call it, this is TA, this will be TW, and this will be TB. We cool?
Yeah.
Alright. TA stands for, that's the tension in rope A, this is the tension in rope B, and this is the tension with the wall. So this first tension that we were talking about was TA. So I'll put a little A over there. Cool?
Yeah.
Alright. Let's add the forces in the Y direction on that knot. On that point that's connecting all those things. Okay?
Okay.
What forces do you see, or what is the acceleration in the Y direction of this thing?
I'm assuming there's no acceleration in the Y direction.
Right, because they told us the whole thing wasn't moving, so there's no acceleration. All right, Julia, I'm asking you to do a few. I'm kind of skipping steps now. What I'm doing right now is I'm trying to train your brain to think of these steps in your head. What forces do you see that's acting on that spot right there that is in the Y direction?
Tension B.
TB. Negative,
And then
right?
the
It's negative, right?
tension, is that tension W, but it's tension W sine theta?
Well, there's no fooling you. That's exactly what it is. Great job. Awesome. Yeah. You know, like I always say, oh, I take a vector and I break it up into its components. You did that already in your head. That's good. If not, I would have written that down on the side. But I mean, eventually, we're going to get rid of the training wheels and we're going to get straight into the big kid physics. But yeah, that's exactly it. It would be TW sine theta. I got a question. Do you know what to do from here? Do you know which direction to take as to what you're trying to solve for?
Well, I mean, so then tension W sine theta would be equal to tension B, and tension B is the same thing as mass B's weight.
Yes, TB is the same as mass B times gravity. We're skipping steps here, but that's good. All right, what else?
And then after you find tension B, well, I'm assuming then if you go and find the forces in the x direction,
All right, some of the forces in the x direction.
You can then narrow down how to figure out tension A.
Okay, there we go. This is 0, right?
Or tension W, yeah.
And then what forces do I see in the x direction? That would be TA, negative, plus TW cosine theta. You got that?
Yeah.
But I know what TW is. TW is MBG over sine theta. Right?
Right.
So I have TA equals MBG over sine theta cosine theta. You see what I did there?
Yeah.
Alright. Running out of room, maybe work up here. Actually, I've got my answer. My answer is, I'll write it up here, mu s equals, I'm just going to write this line down over here, but instead of a TA, I'm going to write what it's equal to. That would be MBG cotangent theta over MAG. The gravity cancels. So really I have mu s equals MB over MA cotangent theta. By the way, cotangent theta is the same as cosine of theta over sine theta. That's just a trig identity, right? So yeah, that's my answer. Let's think about this. Okay? If MB got really big, what would happen to mu s? Actually, first we think about the units. What's the units on this thing? The units on this thing is kilograms divided by kilograms. So that's no units for this first thing right here, right?
Right.
We also have cotangent of theta. The cotangent of theta, angles are measured in degrees or radians, but technically you should not consider them as units. The cotangent of theta is a unitless number as well. So we have a unitless number times a unitless number. We're going to end up with a unitless number, right? That would be like 2 times 3. That's 6, but there's no units on it. So mu is measured, it's saying that mu has no units, which is a good thing because mu is just a coefficient. It's just a number, so it should have no units to begin with. Does that make sense?
Okay, yeah.
All right. If MB got really big, what would happen to mu s? Looking at this equation.
If MB was really big, then the coefficient of static friction would get bigger.
Would get really big because the numerator is getting bigger, the coefficient would get bigger as well. That's saying that if I hung a huge mass over here, I would need a huge coefficient of static friction to make the situation so that it would not move.
Right. That makes sense.
That makes perfect sense to me too. What happens if MA gets really big?
If MA gets really big, then the static friction would get smaller because it wouldn't be necessary for something. It wouldn't be necessary for something really big to keep it still because it's not that big. Anyway, yeah.
Yeah. No. I hear what you're saying. I hear your logic through it. All right. Let's do one more kind of test. All right. What if theta were 90 degrees? Okay. If theta is 90 degrees, the cotangent of theta, do you know what the cotangent of 90 degrees is? I don't expect you to have that memorized.
I'll check.
No. Here, think about this. What's the cosine of 90?
0.
0. What is the sine of 90?
1.
What's 0 divided by 1?
Oh, so the cotangent of 90 is 0.
Yeah, all right. So the cotangent of 90 is 0. So if theta were 90 degrees, then mu of s would equal to 0. Right?
Right.
Does that make sense?
Yeah,
Why?
because if theta were 90, then that tension W would be pulling straight up and down,
Yeah?
and there would really be no force pulling on object A,
Yeah?
and that it would be still no matter what. Or
Okay.
the static friction, there would be no static friction necessary.
There would be no need for any static friction because the TW would kind of take all of the tension B. It would absorb all of that weight. Does that make sense?
Yeah.
All right. One more. Just because well, first of all, that's an awesome analysis. I love that. Second of all, what if theta were 0 degrees? If theta were 0 degrees, then essentially you would have cosine of 0 divided by sine of 0. Cosine of 0 is 1. Sine of 0 is 0. You'd have 1 over 0. What would happen? What's 1 divided by 0?
Undefined.
Undefined, okay. So if theta were 0 degrees, this thing would become undefined. That makes sense to me as well.
Yeah, that makes sense.
What happens is you try to have a line that's super straight, and you hang a mass off of it, and you want to keep it so that theta is equal to 0, which is impossible to begin with. What would happen is, I sometimes do this exercise because I think it's an interesting one, is I have a student stand holding a string, and I'm on the other side holding the string, and I hang a mass in between, and I say, let's make that angle so it's 0, the angle between the string and the horizontal. So I got somebody holding there's a mass hanging off here. Let's make this angle 0, you know what I mean? So we pull that string really tightly, okay? And we're pulling really tightly until our fingers turn white and there's red marks coming on the other side. And it's still not 0, so I said, we need it to be 0. So we pull it really tightly until it starts to get really red, maybe even bleed a little bit. And we're like, come on, make it 0. So now it's cutting halfway into our fingers and we're still pulling really. Actually, we don't do this part, but anyway. The string's gonna break because it's impossible for that tension to be 0, right?
Right.
So essentially, you would have to pull with an infinite force to make that thing 0. That's what that's saying, is your mu would get so big it'd be undefined, because it would have to be so big in order to make that thing, that angle 0, because it's impossible to make it 0. Cool? Does that make sense?
Yeah, definitely.